So we are moving into a new chapter today. Anybody have any questions or anything we need to talk about before we get going? So today, here's our upcoming schedule. Plan on us doing 7.1 and part of 7.2. 7.2 is our last section for test 2. Okay, so then Wednesday, we'll finish 7.2, which won't take us long, I don't think. I think we'll get most of the way through it today. And work on Hawks. So if you are caught up on Hawks and don't want Hawks help, you can leave when we get done with 7.2 Wednesday, that's fine. And then that'll make Monday, which is, let me get the date for you. Let's say the 11th, so the 18th. Will be review day. And then Wednesday, the 20th, will be test 2. For test 2, we've got 4 sections out of chapter 4 with the decimals and percentages, and then the 2 sections, area and volume, out of chapter 6 and surface area, and then these 2 that we're covering this week about probability. So there are 8 sections on there. Not too bad. Questions or concerns on that? It is stuffy in here. I don't know why it's so stuffy. Nothing? Okay. All right, well, let's talk a little probability then. Probability can get really, really tricky. Luckily, we're not getting into anything too deep. So we're going to look at just the real basics in this section, and then talk about there's really 2 different, there's more than that. There's 2 ways of thinking about probability we're going to look at in this section. And then in the next section, we get a little bit deeper, but not too bad. So, new chapter, so we've got some probability to kind of, we've got some vocabulary to kind of talk our way through. Okay. So, got a few terms we need to know here. So the first one is trial or probability experiment. So if we say a trial or a probability experiment, we're just talking about some procedure, some process we're going to go through, and we don't know the outcome until we do our experiment. Okay, so that would be like flipping a coin. We can figure out what our possibilities are. If we flip a coin, we either get heads or tails, but we don't know which one we're going to get until we actually do the coin flip. So that would be a probability experiment or a trial. Okay, the example the textbook gives us here is drawing a number from 1 to 10 out of a hat. So we're thinking we've got a hat with 10 numbers in there. We reach in and we pull one out. We don't know which one we're going to get until we actually do it. So that would be a trial also. Okay. The individual possibilities for what we get when we do our experiment or our trial, that we call outcomes. So for the coin flip, our outcome would either be heads or tails, or drawing a number 1 to 10 out of a hat. Or we've got several outcomes, right? We could draw a 1, 2, a 3, a 4, 5, 6, 7, 8, 9, or 10. We'd have 10 outcomes there. So those are outcomes. And if we list all the possible outcomes we have from a trial or a probability experiment, we get what we call a sample space. Okay. And So the way we do that, we list them all out, we put them inside of brackets, and we separate each one with a comma. Hopefully that looks familiar. We're writing them down like a set. Right? So we write a sample space like a set, and we're just listing all the possible outcomes. Okay. So if we're drawing 1 to 10 out of a hat, our outcomes are the numbers 1 through 10. Okay. That would be our sample space. Okay. So let's see if we can come up with a couple of other sample spaces. Okay, so sample space is just when we list all the possible outcomes of a probability experiment. Let's look at a couple here, a couple other ones. So we want to list all the possible outcomes, make our sample space for these two. A, we're rolling a single die, and if it doesn't specify, we're talking about a 6-sided die. Okay, so if we want to make our sample space, we're going to need a bracket. We're going to separate each outcome with a comma. And if we're rolling a 6-sided die, what possible values could we roll? What are our choices if it's 6-sided die? 1, yeah, 1, or 2, or 3, or 4, or 5, or the biggest one we could get would be 6, right? 6-sided is labeled 1 through 6. That would be our sample space for that experiment. Yeah, because technically, for it to be a sample space, you need to have them listed. Yeah, because our sample space, we got them in brackets, and we have each outcome listed. So, what about B here? Okay, so this one's a little trickier because we've got 2 events happening in each experiment. It says we got birth order gender for 2 children in a single family. So you could write like boy, girl. Okay, we're going to shorten it up. Okay. So I'm going to say that we could have boy, boy, or boy, girl, or girl, boy, or girl, girl. Okay, that'll work for this one. Questions on those? Okay, so that's the idea of a sample space. Just list them all out. Okay, let's do one more. And this is another one where we have kind of 2 events to think about. Okay, so this one says, identify the sample space for tossing 2 coins together. So for each coin, we either get heads or tails. But we're tossing 2 coins, or flipping 2 coins. So maybe we could get heads on both coins, or heads on the first one, tails on the second one, or tails on the first, heads on the second, or we could get tails on both coins. That would be all of our possibilities. If you have multiple things we're keeping track of like this, so like here, heads, tails is not the same as tails, heads. But the things between the commas, it doesn't matter what order you have the things between the commas. So like if you had tails, tails first, that's okay. Questions on that one? I didn't give you many of these in Hawks because the problems with our textbook get really long, like you have a long sample space to list out, and I gave you the shortest ones I could, and I didn't give you many of them, so sorry they're a little bit long. Yeah, that's the sample space. So let's just kind of walk back. We'll get our formal definition for these terms, okay? So we said a trial or a probability experiment is some procedure, some process we're doing where we get a random result, and here random doesn't mean we have no idea about it. It just means we don't know what the actual result's going to be until we do the process. All right, then if we list out all the possibilities for what we get when we do our trial, all those outcomes. Okay. We list them all together, all the possible outcomes we can have, we get what we call a sample space. That's what we just made. All right, we got one more term here, and then we'll be ready to do some probability. It's one more term, and that is an event. So if we're talking about an event, what we're thinking about there is maybe we're taking some group, okay, some subset of our sample space. Usually we're thinking about some outcomes in our sample space that all have something in common, and that's an event. So like if we go back to our coin flipping one here, maybe I want to think about all the outcomes where we have at least one head, right? So that would be this one, and this one, but not this one. So then all the outcomes where we have at least one head, that would be an event. Okay? So that's some subset of our probability space. Okay? We could also think about all the outcomes where we have no heads. Right? That would be just this one, not the other three. So that would be an event. Okay? Okay? So, got all the terminology there. All right, so as we talk about probability here, we're going to have two types. Right? Two different ways of thinking about probability that we're going to look at here. Okay? The first type of probability we're going to examine, talk about how to calculate, is what we call classical probability, or sometimes you'll hear this called theoretical probability. Okay. All right, so the idea here is that we can list out all the outcomes in our sample space, and then we've got some of those outcomes in some event that we're thinking about. Okay. So we just take the ones that are in our event and divide that by the total number in our sample space. Okay. It's not as bad as it sounds. We take how many we're interested in, the ones that are in our event, and divide by how many outcomes there were. Okay. And then one little note here is, in general, when we're dealing with probability, okay, this is not just classical probability, but in general, when we're dealing with probability, our answer is always going to be between 0 and 1. Okay, it can be 0, it can be 1. Okay, and if you think about them as percentages, then that makes sense. So a probability of 0 would be a 0% chance that something happens, and a probability of 1 would be a 100% chance that something happens. So usually we're not talking about anything that has less than a 0% chance of happening. Right? 0 is already impossible. And 100% is absolute certainty, so normally we're not trying to think of something being more than absolute certainty. So probabilities are generally between 0 and 1. Okay, so let's calculate some classical probabilities. They're not bad. They're not bad. Okay. So we just want to take the number of outcomes that are in our event and divide by the total number of outcomes possible in our sample space. Okay. Let's look at this one. This one's dealing with a deck of cards. Okay, so we've got, suppose we're asked to draw a card from a standard deck of 52 cards. We've got a slide that has the cards on it. Okay, and the same thing's in Honks. If you have one of these 52 card problems, you can hover over where it says 52 cards, and it'll pop up the picture of all the cards in the deck, so you don't have to memorize them. Okay. Stretched it out as big as I could make it. Okay. We can kind of see, so 52 cards total, 13 in each suit. And it's got the cards listed out, so let's find some probabilities here. Okay, so A says, what's the probability that the card you draw is red? Okay, so getting a red card is our event. So we're gonna figure out how many ways that can happen and divide by the total number of possibilities. So here we've got 2 suits of red cards. Now we got 13 diamonds if you count them, 13 hearts if you count them. Okay, for a total of 26 red cards. So there's 26 ways we could get a red card. That's the top number and the number of cards in our event out of 52 total possibilities. 26 out of 52. If we write that in lowest terms, it's 1 out of 2. Or it's okay, you can write it as a decimal too, it'd be 0.5. Our classical probability. But B says, what's the probability the card you draw is a diamond? Okay, so if we go back to our picture, count them, we've got 13 diamonds, so 13 cards in our event, right? 13 different ways we could get a diamond out of 52 cards total. This one's 13 out of 52. I think that's 1 out of 4 or 0.25. Okay. So 1/4, I'm just dividing top and bottom by 13 there. If that bothers you, just do 13 divided by 52, you'll get 0.25. Questions so far? Okay, where we're getting our numbers from? C says, what's the probability the card you draw is a face card? And it tells us that's a king, queen, or jack. So if we look, we've got king, queen, and jack in all 4 suits. So 3, 6, 9, 12 face cards in the deck out of 52. So 12 out of 52. Let's see, 6 out of 26, 3 out of 13. Or we have to round a little bit. It's not a nice, neat decimal there. So about 0.23. We round. Okay. D's a little more interesting. D says, what's the probability of drawing a red spade? Okay. So we need 2 things to be in our event. We need our card to be red and we need it to be a spade. But how many red spades do we have? None, because the spades are black. Okay. So we have 0 cards in our event out of 52 cards. So our probability on this one, 0 out of 52, that's just 0. Okay. Impossible. Okay. So keep an eye out for weird ones like that. If you have something that's impossible to do, that's a probability of 0. If you have something that's guaranteed to happen, then that's probability of 1. Questions on those? Nothing? Okay. Let's get away from cards. Let's do one dealing with something else. Get through these here. Oop, always go too far. All right. Look at this one. This one says, suppose you grab a snack from a bag of chocolates that contain 4, controversial word here, caramel, caramel, whatever you prefer, okay, with milk chocolate, 4 peppermint with white chocolate, 6 dark chocolate with mint, and 2 raspberry with dark chocolate. What's the probability that you randomly grab a raspberry with dark chocolate for your snack? So we want the, how many do we have in our event? So how many raspberry with dark chocolates do we have? 2. Out of, we need to figure out how many we have in total. So 4 the first one, 4 the second one, 6 of the next one, and then 2 of the last one. So 16 total. So our probability here is 2 out of 16, or in lowest terms, 1 out of 8, or 0.125. Or 12.5% chance. Okay. Bless you. Questions on that one? Alrighty, so that's classical probability. Okay. The thing about classical probability, if we think back at the bottom, what we're dividing by, we have to know all the possible outcomes. We have to have knowledge of everything in the sample space. Okay. That's not always practical. Okay. So we don't always calculate probability as a classic probability. Sometimes we think about probability the second way we're going to look at. Okay, and that is empirical probability. Okay. So with empirical probability, our formula is a little different. It's the same idea, we're just in a different situation, so our formula is a little different. So what we're doing, okay, we don't necessarily have to know all the possible outcomes for empirical probability. What we're doing is we're gonna just look at some events, okay, look at some outcomes, I should say. Okay? And we look at how many times our event occurs out of how many times the experiment was performed. Okay? So our bottom number here is not all the possible outcomes, this is just however many times we're going to do our experiment. Okay? And again, it's between 0 and 1. Okay? So a little bit different. A little bit different. It works the same way, okay, but what we end up with is a little bit different. Another name for empirical probability, sometimes you'll see this called experimental probability. Okay. So what's going on here is maybe I want to know the probability of somebody's favorite pizza topping being pepperoni. Okay. Then in order to do classical probability, what I would have to do is I would have to ask every person what their favorite pizza topping was. And then take the pepperonis and divide by how many people there were. Right. That's not very practical, right? There are a lot of people alive. So instead what I would do is I would maybe just like ask everybody in this room, okay, what your favorite pizza topping is. Then I could take the people that said pepperoni divided by how many people I asked. Okay? That gives me empirical probability. Okay. So let's look at one of these. All right, this one says, for elementary school science fair project, Libby is conducting research on the accuracy of the weather prediction from her local news channel. She recorded the forecast and the actual weather for 2 weeks. I've got her information on the table on the next slide here. Okay, so left column, we've got the forecast. Right column, we've got the actual weather that day. we'll come back to that. We want to know, using empirical probability, what's the probability that the news channel accurately predicts the next day's weather? Okay. So we want to know what's the probability they get it right. So in order to do classical probability here, we would have to know every time they've made a prediction. Okay. And then we would have to know the actual weather that day. And that could be a whole lot of numbers, right? A whole lot of days worth of weather. Okay. So instead, what we're doing is we're just taking these 2 weeks. We're going to calculate our probability based off of these 2 weeks. So what we want here, we want the days where they got the forecast correct. Okay. That would be our event. And then we're going to divide by the total number of days that we checked. Okay. So here on the first day, rain, rain. Okay, that one matches. Next day it says chance of snow and then rain, so I'm going to skip that one. Then we got snow, snow. And cloudy and clear, that one doesn't match, so I'll skip it. Next one's cloudy, cloudy, so that one worked. Then we got rain, rain, that one matched. We got clear and drizzling rain, that one does not match. Clear, clear does. Cloudy and clear doesn't match. Chance of snow and cloudy, I don't really know what to do with that one, but since it's not an exact match, I'm gonna leave it out. Clear, clear matches. Clear, clear matches. Rain, rain matches. Chance of rain, cloudy. I'm not gonna count it because it doesn't match exactly. Okay. So we want to know how many days they got it exactly right. So what do we have there? 1, 2, 3, 4, 5, 6, 7, 8 matches. Okay. Out of how many we got total? 14. So our probability here, 8 out of 14. That's 4 out of 7 as a decimal. Let's see. You can just do 8 divided by 14, it'll be fine. That's about 0.571. I'm rounding to 3 decimal places there. So if we change it to a percentage, there's about a 57.1% chance they get the forecast correct. That's rounded, but here's our empirical probability. So classical probability is kind of like, in theory, what the probability should be, and then empirical probability is kind of like in practice, how did it work out? Question on that one? Yes. You could leave it as a decimal. You could say 0.571. That's okay. You can do either one. Yeah. Unless the question specifically asks you for a percentage. Yeah. Yeah. Probability, you can write it any of 3 ways. You can write it as a fraction, as a decimal, or as a percentage. They're all acceptable. Okay. All right. So these last few on these, we just want to decide if the situation we're in would give us classical probability or empirical probability. And they can be a little tricky, but let's take a look here. All right, so is this classical or empirical? So A says Katie's curious about her chances of winning an e-reader from the Student Government Association. She polled her friends to find out how many of them filled out the survey to be entered in the contest. So would that give us classical or empirical probability? That one's going to be empirical. Okay. In order for it to be classical, she would have to ask everybody, okay, in the student body if they entered. Okay. But she didn't. She's just taking a poll of her friends. So what she would do here is she would just take how many of her friends said they entered and divide that out of how many she asked. Okay. But that's not counting everybody. So that would not be classical. That'd be empirical. Okay. B says Tristan's interested in his chances of winning at the blackjack table. He determines the probability of what his next card will be by knowing the cards that have already been played. That'd be classical or empirical? That one's going to be classical, a little tricky here, but that one's going to be classical because he knows how many cards are in the deck, what cards are in there. And he knows which ones have been played. So he knows all the cards that are left. Okay? So he knows the whole sample space. Okay? So we could get classical probability off that one. Okay? And then let's look at C. C's a little bit of a gray area here. Okay? I'm not going to give you one that's tricky, I promise. Okay? C says, based on the recent United States Census, the local government estimates the amount of growth the community will experience in the coming years. So I say this one's a little bit of a gray area because the idea behind the United States Census is that we collect data from everybody. That's the idea. Okay? So if that were true, if we did collect data from everybody, then we could call this one classical probability. But do you think they actually get everybody when they did the census? No. So really, in reality, it's really empirical probability. Okay? So at its heart, it would be classical, but in practice, it's really empirical. Okay. Questions on those? Not too bad. Is everybody sleepy already on Monday? Yeah. I actually got to sleep a little late today, so I'm not too sleepy right now, for once. That's always kind of annoying when you're like half sleep zombie and then the teacher's all like energetic. You know? I mean, this is me energetic, not that. So I guess you're safe. Okay. Yeah. All right. So let's get at least part of the way through 7.2. Okay. Section 7.2, we're gonna, it might sound kind of silly, but what we're gonna do is we're gonna look at some different counting techniques. Okay? You might not have ever thought about the necessity for having different techniques for counting. Okay? That's what we're looking at here. Not everything's easy to count. Okay, so the idea is that if we want to calculate a probability, we need to know what number to divide by. Right? We need to know how many things are in our sample space. So sometimes it is easy, right? Like if we're flipping a coin, okay, we just, we're flipping a couple coins, we just count up how many possibilities we have, and that's not a big deal. Okay, but sometimes those numbers can get really big, and would be really tedious, okay, to just make a big, huge, long list of all the possibilities, okay, to count them out that way. So what we're after in this section is we're after ways that we can come up with the number, how many things we'll have in our sample space, how many outcomes we'll have in our sample space without having to actually list them all out. Okay? So that's our goal here. So, if you've got a sample space of 2 million and something, you don't want to have to list all those out. Okay? So that's what we're after here. Okay? All right, so here's our first method, and it's a big one. Okay? It's important. It's got the name fundamental on there. Anytime you see something called the fundamental, something that's important. Okay? Thing's called the fundamental counting principle. Okay? It says we have a sequence of n experiments, okay, where the first experiment has K1 outcomes, the second experiment has K2 outcomes, the third experiment, blah, blah, blah. Okay? Then the number of possible outcomes is just K1 times K2 times K3 till we get to the end. That's all that's saying. So what this is saying is if we have so many ways we can do the first thing, so many ways we can do the second thing, so many ways we can do the third thing, to figure out the total number of ways we can do all of it is we just take those and multiply them together. Okay? Just multiply them together. Okay? So it might look kind of messy on that slide when you write it out, like in the mathematical terminology and all that, but it's an easy idea. It's an easy idea. You just multiply the different numbers together. Okay. We'll see one of those in just a second. Okay. And we've got one other idea that we need to think about here, and that's if we're doing a probability experiment that is going to fall into one of these two categories. Either our experiment we're doing falls into category of with replacement or without replacement. So if we're doing with replacement, the idea here, you can think about like working with a deck of cards. Okay? The idea here is that if we draw a card, after we draw it, we're going to put it back in the deck. Okay, that's with replacement. Without replacement would be if we have a deck of cards and we're going to draw a card, then we don't put it back in the deck. Okay? The issue there is that when we draw our next card, we don't have as many cards in the deck that we're drawing from. Okay? So that changes our probabilities, so we have to keep that in mind. Okay? So let's look at a problem. Okay? All right. It says, in order to log into your new email account, we've got to create a password. The requirements are that the password needs to be 8 characters long, consisting of 5 lowercase letters followed by 3 numbers. So we're making it a little bit easier on ourselves than it could be. Okay, so 8 characters long. The first 5 have to be lowercase letters. The next 3 have to be numbers. If you're allowed to use a character more than once, okay, so like if we pick M as one of our letters, we can use M again. Okay, so this with replacement. We want to know how many different possibilities there are for passwords. So we are replacing a letter or a number after we use it. And then we're going to use our fundamental counting principle here to come up with how many possible passwords there are. Okay. So let's think about picking our first character. Okay. So if we're picking spot number 1, it has to be a lowercase letter. So how many choices of lowercase letters do we have? We got 26. So in spot number 1, we've got 26 choices for what we can pick. Okay. In spot number 2, we can use, even if we used a certain letter for spot 1, we could use it again if we wanted to. We have with replacement. So we need a letter again. How many letters do we have to pick from? 26. Okay, and that's going to be the same for each one of the letters because we're not excluding a character after we use it. So our first 5 characters are all going to be 26 possibilities. 26 letters to choose from. Okay. Now we're through the first 5 that are letters. Now we're on the last 3 that are numbers. So we're picking a digit's what we're picking. Okay, but 0 through 9. So how many choices do we have for picking a digit 0 through 9? We've got 10 choices, yeah. So 0 or 1 through 9, that's a total of 10. For the next one, we can reuse 1 if we need to. So like we could, if we picked 1 as our digit on the first one, we could use 1 again with replacement. So that means we still have 10 choices. And for the last one, we still have 10 choices. And we just multiply all those together. That's our fundamental counting principle here. Okay? So we're going to get a big number here. Multiply all those together. And let's see if I left it in the slides. I didn't. Yeah, okay, good. I don't have to undo the scientific notation my calculator gives me. So here, okay, we got 26 5 times and then 10 3 times. So we end up with 11,881,376,000 possible passwords. That's 26 times 26 times 26 times 26 times 26 times 10 times 10 times 10. I was glad I was in there. Your calculator probably did the same thing. Mine gave me 1.188137 times 10 to the 10th power. I put in scientific notation, so. Did you have any idea it was going to be that big of a number? You didn't think about it? Okay. Hey, let's look at another one. Same idea, but this time we're still doing 5 lowercase letters followed by 3 numbers, but this time no duplicates. Okay, if you pick a letter, that letter's out. You can't use it anymore. Same thing with the digits. Okay? If you pick a digit, you can't use that digit again. So picking our first character, we still would have 26 choices. But whatever letter we pick that time, we can't use it again. So on the next one, how many choices will we have? 25. Then we've got 2 letters we can't use again. So for the third one, how many? 24. Then we got 3 letters we can't use again. So the next one would be 23. And we got 4 letters we can't use again. So the last one would be 22 choices. Does that make sense why we're going down one each time? Because every time we pick one, we've like excluded that letter from the possibilities for the next one. Digits start out the same way, right? We still have 10 choices for our first digit. Whatever we pick, we can't use again. So the next one, we only have 9 choices. And then for the last one, we only have 8 choices. Then we could multiply all those together. And make sure I've got it in here. Yeah, I do. So if we do that multiplication, okay, we get 5,683,392,000 possibilities. So just the simple fact that we said we're not going to reuse a character, that cut our number of possible passwords almost in half. So replacement makes a big difference, okay, if you're doing with or without replacement. Questions on those two? Fundamental counting principle? Okay. That method, okay, with or without replacement, okay, where you just list how many possibilities you have for each thing and multiply them all together, that's going to get you through most of the probability problems in this assignment. Okay? Get you most of the way through. Okay? But that's not always the only thing we need. Okay. Okay. But let's look at the pattern we've got going on here. Okay? So here, if we're doing without replacement, every time we go to the next one, we're going down by 1 number. That kind of pattern ends up happening a lot. So we have a notation that we use to write that down. So like if we wanted to do like 3 times 2 times 1, or 4 times 3 times 2 times 1. Okay, some of you may have seen this before, but that notation we use is called factorial. We use an exclamation point. Okay? So here it says n factorial. That's where we're going to start with the n and count our way down until we get to 1, and we're multiplying all those together. So n factorial would be n times n minus 1 times n minus 2 times n minus 3, all the way till we get down to 1. That's n factorial. Okay. And got an important thing here on this last slide, and it doesn't really make sense, okay? But 0 factorial, okay, by definition, 0 factorial is going to be 1. There's several arguments on why we use it. So it could be like, how many ways can you pick 0 things? Right, it'd be 1 way. None of them. Pick none of them. But you can just take it by definition. It's okay. So let's work with these idea of factorials a little bit. Okay? Anybody seen factorial thing before? No? Okay, yeah. You don't get to it a lot in high school, so sometimes there's a few people that have seen it a little bit. Okay. Let's work with these a little bit. Okay. Some neat things happen when you start working with these expressions. So we've got 5 different factorial expressions we want to simplify. Okay? So each one of these should just simplify to some number. Okay? So let's do A. And I've got the other ones on their own slides. Okay, so if we do A, we want to simplify 8 factorial. So 8 factorial means 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. Okay. What 8 factorial means. So we can just multiply all that out. Okay. Some of your calculators probably have a factorial button. If you can find it on there, it's exclamation point, but a lot of them won't. Okay, it just depends on your calculator. You can just do this a long way. Okay, so for this one, I get 8 factorial is 40,320. Okay. 8 factorial. One thing about factorials that's kind of interesting is that they get big really quickly. You probably, not lately because it hasn't been so bad, but you've probably heard people talk about exponential growth before. That means something's getting big really quick. If it's growing exponentially, that deals with the exponent on a number. Factorials grow even faster than exponents. Okay? So factorial growth would be way bigger than exponential growth. There's some, if I remember it exactly, there's something like, if you have a checkerboard, it's got 64 squares on it. Okay, it's 8 by 8. So if you start on the first square and you put 1 factorial pennies there, right, that's 1 penny. On the next square, if you put 2 factorial, that'd be 2 pennies, 2 times 1. The next square, if you put 3 factorial pennies, that would be 6 pennies, right? 3 times 2 times 1. But by the time you get to the 64th square, if you did 64 factorial pennies, that's like more pennies than it would take to get to the moon. Okay. So it grows really quickly. So, okay, there's A. Let's look at B. Okay. B, we've got 3 factorial over 0 factorial. So 3 factorial is 3 times 2 times 1. 0 factorial, do you remember what it is? 0 factorial is just 1. Okay? So this thing just turns out to be 6. C gets a little more interesting. Okay? C, we've got 89 factorial over 87 factorial. Okay? Those are huge numbers. Okay? If you try to put 89 factorial into your calculator is going to pitch a fit. Okay? It cannot handle a number the size of 89 factorial. Okay? That's how big that number is. But we're smarter than our calculators. Okay? So we can actually figure this out. Because there's a neat little pattern here that happens. Okay? So if we do 89 factorial, that would mean 89 times 88 times 87 times 86 times 85, all the way down. We would end up, on the end, we would end up with 3 times 2 times 1. So I'm skipping in the middle. But then what we have on the bottom. What we have on the bottom. 87 factorial, so 87 factorial would be 87 times 86 times 85 times 8, and then on and on and on down to 3 times 2 times 1. So, you may notice anything that's going to happen here? What happens if you have some number over itself? Cancels. All these are multiplied together so we can cancel. So what cancels? Yeah, almost everything. Yeah. 1 over 1 cancels, 2 over 2 cancels, 3 over 3 cancels. All this stuff in the middle that I don't have written down would cancel out. Right? 85 over 85 cancels, 86 over 86 cancels, 87 over 87 cancels. So all we're left with is 89 times 88. That's not too bad. That's 7,832. So be looking for that when you're working with these factorials. And, remember, you're going to have that little pattern there, and once you get down to where they start matching up and you've got the same thing on top and bottom, all those are going to cancel. If you're a nerd, that's kind of cool. Okay. It's all right if you don't think it's cool. All right. Questions on that one? Got the canceling idea? Let's look at D. D says we've got 7 factorial over 5 minus 1 factorial. So the first thing we want to do here is we want to do the subtraction. So 5 minus 1 would give us 4 factorial. Okay. So then on the top, we've got 7 times 6 times 5 times 4 times 3 times 2 times 1. On the bottom, we've got 4 times 3 times 2 times 1. And even though this one's not as long, we still have stuff that cancels. Right? What cancels? The 4s, 3s, 2s, and 1s. So what are we left with? Just 7 times 6 times 5. Is that 210? Yep, 210. Okay. One more. Okay. E. Okay. Almost the same thing, but it gives us 2 different factorial terms on the bottom. Okay. We still want to start off doing this subtraction in the parentheses, so that's going to be 3 factorial times, and then 4 minus 2 would be 2 factorial. That's okay. We still can just list it out. So 5 factorial, 5 times 4 times 3 times 2 times 1. On the bottom, 3 factorial, 3 times 2 times 1, times 2 factorial, which is 2 times 1. And then just cancel out as much as you can. Okay. Here I'm going to do the 3, 2, 1 with the 3, 2, 1. So what are we left with? On top, we've got 5 times 4. On bottom, we've got 2 times 1. That's 20 over 2. 10. Okay. Any questions on those? Nothing? You good? Hanging in there? All right, so that's a good stopping place, I think. Okay. Wednesday, even if you don't have Hawks to do, try not to miss Wednesday, okay? Because this last little bit you want to get, okay? You don't want to miss it. Okay. And then you can leave after we get that part done if you don't want Hawk's help, okay? I will bring candy Wednesday, how about that? Okay, we're getting close to Halloween, so I'll bring us some candy to help entice you to come, okay? Yeah. If you didn't get on the sign-in sheet, make sure you get on there before you leave. And I'll see you Wednesday.